Inverse functions, we had a bit of a look at this last year, you may remember, back when we were doing functions right at the start of the year. I said don't worry too much about it, we're just having a taste because next year we'll revisit it. Here we are, revisiting. So a reminder of what they were about. Y equals function x is a function. Well, we know the definition of a function. We know that for every x in the domain, there's at least one y value. We can use the vertical line test to visually see if it's a function, that sort of idea. Okay. Now, the relation, if we swap the x and y's around, now this stage is just a relation. We don't know if it's a function yet. So we just swap the x and the y's around. We now have x equals function y. We may or may not make y the subject. I guess it just depends on how easy it is with the new function. But so for example, if we have y equals x cubed plus x, its inverse relation is x equals y cubed plus y. Swap the x and the y's around. Bit hard to make y the subject of that one. Okay, so we've now got a new relation. But if that new relation, for every x value in the domain, there's a maximum of one y value. In other words, the new relation is a function. Then it becomes an inverse function rather than an inverse relation. Visually, if I want to just look at the original curve, instead of using a vertical line test, I can use a horizontal line test. And if it satisfies the horizontal line test, then I know the new relation, when I swap the x and y's, will actually be a function. And then we can call it an inverse function. If you think about it, most things won't have an inverse function unless it's continually increasing or continually decreasing. Because as soon as you have a turning point, it's going to fail a horizontal line test. And when you think of all the different types of curves and graphs, most of them have some sort of turning point in there. So it's probably more the minority that have an actual inverse function. Symbolized, f with a negative 1. Now that does not mean reciprocal. That does not mean 1 over. It's just negative 1 for inverse. Okay. If we were to draw both of them on the number plane, then they would be reflections of each other in the line y equals x. And that's because you've swapped the x and the y values around. So if you were to turn your head 45 degrees, you go, oh yeah, look at that. Trust me, you would. Exactly that's what you'd say. So if AB is on the original curve, then BA will be on the new curve. The x and the y swapped around. Okay. The domain of the original curve becomes the range of the new curve. And the range of the original curve becomes the domain of the new curve. So, testing for inverse functions. As I said, you could use a horizontal line test. That's the quickest way to just visually see, yep, that's going to have an inverse function or not. So, y equals x squared. There it is. We have a look at it and go, will that have an inverse function? No. Look, cuts it twice. No good. So it'll have an inverse relation, but not an inverse function. What about y equals x cubed? Yes, it would. Doesn't matter where I put the line, it'll only cut it once. So, yep, that will have an inverse function. So that's visually. But I could check with algebra as well. So if I swap the x and the y's around and try and make y the subject. Now, if when I'm doing that, I come up with something that's unique, i.e. there's only one possible answer, then it's an inverse function. But as soon as I hear myself saying things like plus or minus, that means there's two possibilities. So if we have a look at our parabola, I swap the x and the y's around, so x is y squared. Well, if x is y squared, y is plus or minus the square root of x. So there's two possibilities. So it's not an inverse function. Right? Not unique. No. Whereas our cubic there, x equals y cubed, y is the cube root of x. But it is a unique answer. So yes, that one's fine. If the inverse relation is a function, in other words, it has an inverse function, then These sorts of things should happen because inverses cancel each other out. That's why when we're trying to solve an exponential equation, we log both sides, because the log is the inverse function of the exponential. You do the inverse to undo it. So if I sub the function into the inverse, I should get x. If I sub the inverse into the function, I should just get x. So here's my original function. Let's try and find the inverse. Swap the x and the y's around. Make y the subject. Just a little bit of manipulation, but there it is. 3x minus 1, 2x plus 2. Okay. If I sub the original function into the inverse, so everywhere I see x, I'm replacing with 2x plus 1 on 3 minus 2x. Well, again, bit of algebraic manipulation, but yeah, we end up with x. And the reverse should work. If I substitute the inverse, so now everywhere I see x in the original function, I'm going to replace it with the inverse, 3x minus 1 on 2x plus 2. If I expand that one all out, yep, I get x. But as I said, most functions won't have an inverse function. So for it to be useful, what we end up doing is restricting the domain. And we just pick a piece of the original function that will satisfy that horizontal line test, if you like. So we're going to restrict the domain. Now, so what I was saying is, when you try and capture your piece of your function, you want to get as much of the range as possible. Hopefully you can get all the range. Y equals x cubed, we know there's not going to be an issue here because it has an inverse function. So let's go back into our beautifully drawn y equals x cubed. The domain is all real x, okay? The range is all real y. Watch that. What happens when I swap them round? Right, x is y cubed, so y now becomes x to the power of a third. The domain of the new function is now all real x, which was the old range. But the range of the new function is all real y, which, yeah, I really should get a better example. But theoretically, they've swapped. The domain and range have swapped. Yeah, let's look at the beautifully drawn y equals x to the power of a third. And sure enough, remember what you do? You turn your head 45 degrees and go, wow. That's it, very good. Okay. Y equals e to the power of x. We know what that one looks like. It's our exponential curve. Okay. Domain, all real x. Range, y is greater than 0. Swap the x and the y's around, so x is e to the y. To undo the exponential, we log both sides. So y equals log x is the inverse. The domain of the log curve is x is greater than 0, which was the range of the original function, and the range of the new function, all real y, was the domain of the original function, thus highlighting how the x and the y's swap around. That was a better example. There's the reflection. Now this one is good for what I'm talking about, was restricting the domain. We know y equals x squared doesn't have an inverse. Right? Domain's all real x, range y greater than or equal to 0. We know there's no inverse, but we want to find an inverse function we can use this with. So we're going to restrict the domain. I've chosen x is greater than or equal to 0. Because x is greater than or equal to 0, the range will still be y is greater than or equal to 0. Yeah? So I've managed to capture the whole range. So I've chosen that. I suppose I could have picked x is less than or equal to 0, but usually we try and get the positives if we can. So my new function will be y is x to the power of a half. But that, of course, is positive square root, not the negative square root. Domain is now x is greater than or equal to 0, which was the range of the original function. But the range of the inverse is the restricted domain that I chose. So if I was to draw it, it's just the top half of the parabola. So y equals x to the power of a half. All right, 2010 paper. There's our function, e to the minus x squared. Actually a very important function in statistics. It's what we call the...
Bell curve.
Oh yeah, bell curve. I was thinking the normal curve. Normal curve isn't actually minus x squared. There's another coefficient in front of it, but it's very similar to the normal curve. Okay, the graph has 2 points of inflection. Find those x coordinates was the first part of the question. So okay, we know the possible ones occur when the second derivative is equal to 0. So I find my second derivative and solve when that's equal to 0. Now, I don't have to test.
Because you know there are 2.
Yeah, because they told me there was 2 and I came up with only 2 possible answers. So they must be the 2 that they're looking for. And they've only asked for the x coordinates, so I'm not going to worry about finding y coordinates. Okay, explain why the domain must be restricted. Well, okay. I used some technical words there, but in order for an inverse function to exist, there must be a one-to-one relationship. In other words, for every x value, there's a maximum of one y value. But that's what they're looking for, basically. It needs to satisfy it. Satisfies the horizontal line test, or in this case, doesn't satisfy the horizontal line test. Find the formula. Okay, swap the x and the y's around. And there we have a y equals plus or minus, so that's another reason we know there's no inverse, the square root of the log of 1 on x. Now, the domain of the original function becomes the range of the inverse. So they've told me we're restricting the domain to x is greater than or equal to 0, therefore the range of my answer must be greater than or equal to 0. So which one do we pick?
Oh,
Said so enthusiastically there. So we have y equals the square root of log 1 on x. State the domain. State the domain. Well, the range of the original will be the domain of the inverse. And so if we look at that original graph, 0 is less than x is less than or equal to negative 1. Sketch the curve. Ta-da! You like my sketch? I honestly didn't just rotate the original picture. Ta-da! But it should be a reflection in y equals x, basically. The x-intercept, the y-intercept became the x-intercept. It was going asymptotic to the x-axis. It's now going asymptotic to the y-axis, etc., etc.